Okay, this is part one of today's lecture. Let's start to go through the basics of musical instruments. Okay, we'll begin with stringed instruments. Stringed instruments are the most versatile of musical instruments. That is, they can produce a very rich and wide variety of notes. Okay, so let me immediately demonstrate stringed instruments to you by means of my rather poorly made guitar. So this guitar consists of 4 guitar strings of varying densities that are all held under tension by the pegs on opposite sides of the guitar, and then the body of the guitar is just a 2x4. Okay, now what I'm going to do is go ahead and pluck one of the strings. I'm going to do so rather hard, like so. Like so. And now when I do pluck that string particularly hard like this, you kind of hear that annoying high-pitched twanging sound. That annoying high-pitched sound comes from a very complicated waveform of a very high frequency that forms on the guitar string. However, that waveform damps out fairly quickly, and the tone that persists is just simply the n=1 standing wave. So for example, I can demonstrate that for you here. Hopefully the microphone will pick it up if I pluck the guitar string rather softly. Like so, okay? All right, so first of all, let's say that we pluck a guitar string hard. And when you do, you end up with this really high frequency complicated waveform like so, that forms on the guitar string itself. Okay, usually this high frequency waveform damps out quickly. And the tone that persists is just simply the n=1 standing wave. So recall from the previous chapter that that standing wave then, one antinode, looks like this. Like so, and then 1/2 period later, the standing wave oscillates to here. Here's one guitar peg, here's the other, those are the location of nodes, right here is the location of the antinode, and then just like we did in the previous chapter, we labeled the distance from node to node here, from peg to peg in the guitar, we label that as L. Okay, now recall that in this space L, for the n=1 standing wave, as you can see, you have here 1/2 wavelength. And then recall the little pattern equations from standing waves that we did see in the previous chapter. So for standing waves in the space L, we have to have multiples of half wavelengths. This right here, obviously, once again, is n=1. And then the harmonic frequencies, hence the connotation with music, the harmonic frequencies are governed by the following expression. We also saw this back in the previous chapter when just talking about standing waves themselves. Okay, now when n=1, the frequency that you're hearing here is then therefore the fundamental frequency, also known as the first harmonic frequency, is the quantity of V/2L. So notice that you can change a number of the parameters here associated with the right-hand side of the expression to play different notes. The easiest thing to change, for example, on a single guitar string is the length of the string L. So listen to what happens with my guitar when I make the L smaller. When I make the L smaller, the frequency is going to be higher. It's going to be a higher pitched sound. So once again, before I do this, like so, string sounds like that. But now I'm going to go ahead and pinch the string down to the fretboard like this, and then pluck it over here. When I do, this portion of the string does not vibrate at all. So now the distance L is simply from here to here on the guitar string, and then therefore you end up with a higher pitched sound. Like so. So on a single guitar string, that's obviously the easiest way to change the note that is being played by adjusting the L. You could also, however, adjust the speed. This speed right here is not the speed of sound. It's the speed of the wave on the string itself. It's the speed of the wave on the string. So from basic wave dynamics, that speed is governed by the following expression. The square root of the tension divided by the linear mass density. So I can then therefore change the speed of the wave by adjusting these parameters here. So for example, I'll once again use my single guitar string in just a moment, but now what I'm going to do when I pluck the string is I'm going to change the tension. So before I do this, for example, the guitar string sounds like this. But then after I change the tension, I'm going to go ahead and tighten up the pegs here in doing so, like so. Now if I increase the tension, I increase the wave's speed, and then therefore I increase the frequency. Like so, higher pitch than it was a moment ago. You could also, of course, go from string to string. When you go from string to string, strings have different thicknesses associated with them. This then means that they have different densities. So you're basically playing around with this variable when you're going from string to string. So basically with a stringed instrument, just from this one expression, you can control three things. The easiest thing that you can control is the length of the string that's being played. You can also adjust the tension. You can also move from string to string. So this is why stringed instruments in particular are so versatile. Skilled players of guitars, especially such as, for example, electric guitars, skilled players can play some of the higher harmonics. For example, let's take a look at the n equals 2 standing wave. And for the n equals 2 standing wave, when n is equal to 2, this then means that in the space L you have a full wavelength. You have two antinodes, if you remember. It looks like this. Here's the space L, and then a half a period later, it oscillates to here. So the way that you would play this is to pinch the string sideways with your finger right here at the location of this node. So you don't press the string all the way down to the fretboard when you do this. You basically just pinch the string from the side. Skilled players can do this on electric guitars, in particular using different types of effect pedals and so on and so forth to elicit different sounds, to elicit different frequencies. So I can do that on this guitar. And by the way, in this case, what I'm going to do is place the guitar on the table. When I do, I'm going to amplify the sound, by the way. I'll describe how that occurs in a little while. Like so. And now what I'm going to do is take my finger here and pinch the string from the side. So when I pinch it from the side, both sides of the string now do vibrate. It then looks like this, and it's the n equals 2 standing wave. So it's going to be a higher pitched sound than it was a moment ago. It doesn't sound all that great, however, on this guitar. Like so. So there are some skilled players that could play the n equals 2, and in some cases the n equals 3 standing wave by placing their fingers in different positions here along the fretboard. Okay, now how do you amplify the sound associated with the guitar? If I just hold the guitar by itself, as I indicated earlier, and as you heard earlier, it doesn't sound all that great. Like so. Well, when I pluck the string, not only does the string vibrate, but the entire body of the instrument vibrates. The entire guitar vibrates. So then therefore you have sound waves coming off of, or generated by, if you will, the vibrating string and the vibrating board. The board vibrates at the exact same frequency as that of the string. The easiest way to amplify the sound, quite simply, is just increase the surface area of the instrument. If you increase the surface area of the instrument, then therefore the amplitude of overall the sound waves that are being generated here by the vibrating instrument is greater. So I'm going to do that like I did a few minutes ago by placing the guitar here on the table. So now when I set the guitar string into vibration, not only does the board vibrate, but the table vibrates as well. And then therefore, of course, it's a lot louder than it was before. I can also do this, by the way, with my tuning fork. So recall this tuning fork from a previous lecture, for example. I'm going to give it a good whack. Okay, you hear that high-pitched sound initially. That comes from, once again, a very high-frequency, complicated waveform that forms on each individual tone. but the tone that persists is just simply the fundamental frequency associated with each tongue as a vibrating stick, like so. You'll be able to hear that now if I amplify the sound by taking the tuning fork and placing it on the desk. Like so. So not only is the tuning fork vibrating, but also in addition to that, the entire table was vibrating, okay? Okay, at this point, let's go ahead and start to take a look at the lecture examples. So in order to do so, at this point, access those lecture examples in the folder and copy down the first of those examples. It's over here on my screen. Okay, so a guitar string has a length of 0.5 meters. The string vibrates at 440 hertz when plucked. Those of you that know anything at all about musical instruments and scales and octaves and so on and so forth may recognize that as a specific note. Okay, where must you place your finger to play 528 hertz, which is also a well-known note. At any rate, however, here's what we have in the problem. So we have here the length L1, I'm going to call it, is 0.5 meters associated with the guitar string. Okay, here's the guitar string vibrating like so as a simple picture. Here's the distance L1. Okay, the frequency associated with it, call it F1, is 440 hertz. Okay, now we're going to place our finger to get a second length here, L2, such that we then play a frequency here, F2 we'll call it, of 528 hertz. Okay, for both of these frequencies, they are fundamental frequencies, so then therefore it's this expression here when n is equal to 1. And now what I'm going to do is just write down this expression for the two frequencies that I have. So for example, F1 is going to be V over 2 times L1, and F2 is going to be V divided by 2 times L2. The speed of the wave on the string V is the same for both of these frequencies, because ultimately that speed is controlled by the tension. You don't change the tension in the string by just pressing the string down to the fretboard. So then therefore, when I end up here, basically it's just with two equations and two unknowns. The two unknowns are the speed V, which we're not concerned with, and the length L2. What you'll find about this example and the ones that follow is that sometimes these types of problems are most easily done if you just take one expression and divide it by the other. So I'm going to do that here. So for example, I'm going to go ahead and take F2 and divide it by F1. So then V over 2 times L2 divided by the same V over 2 times L1. And then on the right-hand side of the expression, a bunch of stuff cancels out. So the 2's cancel, the V's cancel like so. And then if you rewrite the expression here on the right-hand side carefully, you end up with L1 over L2. And now what I do is I take this portion of the expression and I then just solve for L2. So take the L2 and move it over here to the left-hand side. Take this ratio of frequencies and then move it over to the right-hand side, like so, and now we just multiply out. Simple as that. Okay, so F1 from the board above was 440, and then divided by 528 hertz. Notice that the ratio of frequencies here is less than 1. This then means that the length L2 is going to be less than L1. And then multiply by 1/2 meter, and this comes out to be about 0.42 meters, 42 centimeters. So in terms of a simple demonstration, if we think of my guitar string like so as 50 centimeters long, 0.5 meters, and it then sounds like this, like so. Now I'll go ahead and place my finger here, and then the 0.42 meters, the 42 centimeters we just calculated, is from here to here, like so, and that then gives us this sound, like so, okay? Okay, at this point, go ahead and copy down the second problem. The second problem from the lecture examples gives you an idea as to what happens when you tune an instrument. Okay, now for those of you that do play a string instrument, what you will find every so often, of course, is that you have to retune the instrument. The reason why is because the mere act of playing the instrument then very slowly causes the pegs here holding the string in place to twist a little bit. This adjusts the tension. When that occurs, this then means that the speed of the wave on the string changes. Therefore, the frequency changes. So periodically you have to retune the instrument for that reason. The mere act of playing the instrument will slowly bring it out of tune. Those of you that do play a stringed instrument will also notice that you have to retune the instrument after there has been a wide swing in temperature. Because, for example, if you have really cool weather, this then means that the overall volume of the instrument itself decreases, it contracts when it's cold, and that then changes the tension. If it's really warm outside, if it's really hot, this then causes the instrument to expand. That also then changes the tension. It causes the pegs on this guitar, for example, to slowly twist around. So if there are wide swings in temperature, you immediately have to retune the instrument. At any rate, however, you don't really have to change the tension all that much in order to bring the instrument into tune, and this is then what the second example here is referring to. Okay, so a guitar string is plucked and it vibrates at a fundamental frequency of 435 hertz. By what percentage should you adjust the tension to now bring the string back into tune at 440 hertz? So like in the last example, I'm going to label these frequencies 1 and 2. So we'll say that F1 is 435 hertz, this is out of tune, and then F2 is 440 hertz, this is back into tune. Okay, now I'm going to once again write the fundamental frequency expression where n is equal to 1, but now I'm also going to substitute the following in for the speed v. Like so. In this problem, the L and the mu will stay the same. We're not adjusting the length of the string, and it's the same guitar string, so the mu is the same. In this case, what we're going to be changing is the tension. So I'm going to write the expression here for both F1 and F2. So F1 will be 1 over 2L times the square root of a tension T1 divided by the density mu. And then F2 will be 1 over 2L multiplied by the square root of a T2 now, divided by the same mu. And then, like I did in the first example, what I'm going to do here is just take one of the frequencies and divide it by the other. It really doesn't matter which way you do this. So I'm going to go ahead and take F2 and divide it by F1, like so. So what I do on the right-hand side of the expression, I have this for F2, and then this for F1, and then at this point a bunch of stuff cancels out. So the 1 over 2L cancels like so, and then underneath the radical sign, the mu's cancel like so. If you then simplify what's left over here on the right-hand side, you end up with this. So now what I'm going to do is take this portion of the expression and square it such that I get rid of the radical sign. Like so. And now let's just go ahead and calculate this ratio of frequencies then and square it. In order for you to picture the solution here, however, I'm going to do one extra step. Let's take the tension T1 and just move it up to the left-hand side. So then therefore T2 is equal to the following expression. So it's going to be in terms of T1. The number that we obtain here in front of the T1, that will then allow us to answer the question in terms of a percentage. All right, so I'm going to take 440 and divide it by 435. And then square that, and then I end up with about 1.02 or so as this ratio, like so. So then therefore the tension T2 that we want for 440 hertz has to be 2% greater than the tension T1 associated with the string out of tune. So you only have to change the tension here by 2%. That's why you only have to make minute adjustments when retuning your string instrument, okay? Okay, and then lastly, for the quantitative examples, at this point, go ahead and copy down number 3. We're just going to look at the pattern associated with these harmonic frequencies. Okay, so for the third and last problem for the lecture, 2 successive harmonic frequencies of a guitar string. There's 360 hertz and 420 hertz. What is the fundamental frequency? Okay, now I have here 2 frequencies. Let's call the first one here F1, which is 360 hertz, and that is then going to equal the following expression, where we don't know what the value of n is for this particular note. But it does say in the problem that the next harmonic frequency, it says that they're successive, the next harmonic frequency, F2, which is equal to 420 hertz, well, that then has to be one value greater than the previous n, because they're successive. So I'm going to write this then, therefore, as n plus 1 divided by v over 2L. And then basically what you end up with here are two equations and two unknowns. One of the unknowns is n, which we're not so concerned with, and the other unknown is the quantity v over 2L. V over 2L is the fundamental frequency. That's what's being asked for in the problem. The easiest way to do this example is just to take one frequency and subtract it from the other. So what I'm going to do is F2 minus F1. Like so. And now over here on the left-hand side, we just have 420 minus 360 hertz, which is a total of 60 hertz. Like so. But now watch what happens here on the right-hand side of the expression. We have nv over 2L minus nv over 2L, which drops out, and then we're left with 1 times v over 2L. Like so, which is the fundamental frequency and is then therefore the answer. Okay, looking at the two frequencies that we have here, 360 hertz and 420 hertz, it's obvious that they are both multiples of 60 hertz. 60 times 6 is 360 hertz, 60 times 7 is 420 hertz. So with a problem involving successive harmonic frequencies, mathematically we just subtract one from the other. Okay? Okay, I'm going to go ahead and conclude this right here as a part 1. Part 2 is going to be a very short video. I'll go ahead and get to that next.